what we want to do now, I mean, we do know how to move forward in time, and we do know how we can write down the distribution at every single time given the input. But the point that we want to do is that we want to just build one reverse process. And this process is able to look at every single time, and then you're going to sample from the previous time for us, right? Now, one thing that I'm going to indicate, I want to indicate again, that this guy, this P, is going to be generally depending on time as well, right? So if you want to think about it in form of a neural network, you could say this is one network like this. So any network it could be, and then this guy is taking time, t, and also xt as input. So there could be a bunch of layers, anything that it compute. Then at the output, you're going to have a bunch of output. You're going to pass it through a softmax, right? And this guy is going to give you distribution, right? Distribution of, this is going to be p of xt minus 1 given those things that you had, right? So this is the kind of network that you want to train right now, right? And the thing that you want to have is that this network in total, every single time that you are sampling, this guy is giving you marginally the same distribution as you had when you were moving forward, right? Everybody's cool? Okay, so that is what I want to do. Now, if I want to do that, then what I want to happen is that, for example, when I am at time t, and I move with this model, this neural network, I move one step backward, that new sample at time t minus 1 is marginally distributed as the one which I had when I was moving forward, right? This is what I want to happen, right? Because if this is marginally the same, the previous one is marginally the same, and so on, then the first one is going to be marginally the same as the last sample I get in my reverse trajectory, right? This is what I want to do. So what I want to do, I want eventually to find out what is the marginal distribution at time t minus 1. So one thing that you can do, you can write down the distribution at time t minus 1 in terms of the distribution at time t and this particular model that you have by marginalization, right? So distribution at time t minus 1, this is going to be the distribution of t minus xt minus 1 and xt when you marginalize it over xt, right? And how you can write down this joint distribution is going to be distribution at time xt times distribution at time t minus 1 given xt, right? This guy is given by your model. This guy is the one which you sample initially from. What is in practice this p of xt? Any idea? Any guess? What would be this distribution? Gaussian, right. So because when I move all the way towards the end, then I start sampling from a Gaussian and I want to generate a data, right? So this guy is a Gaussian distribution. This is my model. I can compute this one, right? Supposedly, right? I can compute this one. Everybody's clear? OK, so this is the distribution that I have at time t minus 1. And I'm showing it by p hat because I'm using a model, right? I'm using model pw. This is not necessarily the same thing that I had in forward direction because it might be that my model is not good enough to really realize that distribution, right? But my objective is that this happens, right? Now, what's going to happen if I move all the way backward to the beginning of time? How can I write down the marginal distribution at the very beginning of time when I'm moving all the way backward? It's a kind of a massive marginalization again, right? What I can say, okay, the distribution I get at time 0 is going to be the joint distribution of x's from 0 to t when I marginalize it over all the x's but x0, right? This is the marginal distribution that I get, right? Everybody's clear? Now, what is that joint distribution? Can you help me writing that one down? remember, we are moving backward, right, on the trajectory. My model is able to give me, this is PW of xt minus 1 given xt, right? This is my model. Now, if I want to use this model, how can I open up that joint distribution? Exactly. So you're going to start with pxt, right? This is the one which you sampled, right? Then the next one is going to be p of xt minus 1 given xt, right? What would be the next one? t minus 2 given xt minus 1 and xt. Should I keep xt here? No. Why? Yeah, but if I want to write down the accurate chain rule, then I need xt as well here, right? Correct? But I can ignore it. Why? No, it's not about small. Because I'm using my model, right? My model is describing a Markov chain, right? It's not generating xt minus 2 given xt and xt minus 1. It just looks at xt minus 1, right? And then it generates xt minus 2, correct? So it's a Markov chain. So that guy is going to disappear because I am moving on a Markov chain. You see it or not? How does my model generate? My model generates like this. Push it a bit up. My model generates like this. So we're going to start from xt, right? And then it's going to pass it through p of pw of xt minus 1 given xt, right? Then it's going to sample 1 xt minus 1, right? Now that it samples this guy, now I again pass it through p of xt minus 2 given xt minus 1, and then I'm going to get xt minus 2, right? So when I am generating xt minus 2, I do not give xt to my model, right? Because of that, xt minus 2, given xt minus 1 and xt is described by only xt minus 1. Everybody seeing that? Everybody's cool? If you are cool, what would be the next term in this chain rule? The next term should be p of xt minus 3 given xt minus 2, xt minus 1, xt, but only xt minus 2 is going to remain, right? Because it's again a Markov chain. Going to be xt minus 2, right? And you can keep on going like this. Everybody's clear? You got the idea or not? No question? Okay. So what I can do, I can say that this guy is eventually pxt, pxt minus 1 given xt, pxt minus 2 given t minus 1, and so on until I end up with the very first one, right? x0 given x1, right? Exactly the way that I built my reverse Markov chain, right? Everybody's clear? And now I can just simply factor out things, so I can write it down in this form. So I start from xt, and then every single time I just multiply it to the model distribution of xt minus 1 given xt, right? And this is going to be the joint distribution. Now if I get this massive joint distribution, and if I could integrate it over x1 to xt, capital T, then I'm going to end up with only p of x0, right? And this is going to be the distribution that I see when I move backward with my model on the reverse Markov chain, right? And on the reverse Markov chain, I'm going to move backward, and then I end up with x0 to be exactly this distribution, right? Everybody's clear? Question? No question? Okay, so if there is no question about that, then let's just look at this thing that we found. So say I have one particular sample, right? One particular sample, x0j. And this is my data sample. Now I start from a Gaussian distribution, okay? I sample from it. I give it to my model. I get the previous time. I give it again to model. I get the previous time, so on, till I end up with the first time, right? x0, t equal by 0. Now the thing that I want is that I see exactly this guy, right? So this means that I want the distribution given by my chain rule be exactly same as the distribution that I have on the data set, right? So when I just move backward in time and I end up at time 0, I want that distribution to be exactly same as my data distribution, right? So I could say that I want the KL divergence between the chain rule distribution and the data distribution to be 0, right? If you want to do that, how you can do it in practice? If you want to minimize the KL divergence, you do the maximum likelihood, right? You're going to get the distribution that you have written, that backward distribution, right? The chain rule distribution, p hat 0. You're going to write it down. You can compute it as at one particular point x0, right? You're going to put x0j exactly in that expression, and you try to make it maximum, right? You make it look like maximum on the data points that you have, right? And you do know that if you do this, then you are implicitly minimizing the KL divergence, right? So the solution is simply given by maximum likelihood. So I want to just maximize the likelihood of my model. This means that I'm going to write down this massive chain rule that I have. I integrate it over everything that I have in this expression. Only I replace x0 with x0j, right? And then I compute it at all the data points that I have. Then I have my log likelihood. I sum them up. I want to maximize this one, right? This is the maximum likelihood that we have done in the entire course. Everybody's clear? Questions? No question? Okay. So I want to do this. If I can do this, then eventually, supposedly, this PW is going to be trained in a way that this P0 hat is going to mimic or approximate the data distribution, meaning that when I just move on my chain rule, I end up with a data sample, right? Okay. Now, this is what I want to do at the end of the day. I want to do maximum likelihood on this reverse trajectory, and this is simply written in this form, right? So I need to just write down my model, and then I just compute all of this long, chain rule, and then I want to integrate it and maximize it. Right? But do you think this is a kind of feasible task to do? Just to give you a rule of thumb, I mean that capital T, the length of the Markov chain, is typically in the order of 1,000. If it is in an order of 1,000, then you need to just integrate over 1,000 different variables, right? And all of them are supposedly of the same dimension as your data, right? Like all of them are same resolution images as the image you want to generate. Can you do this calculation? No, this is a massive computation, right? So this guy is quite massive, right? So we cannot really do it, but we get around this issue quickly. Now, one thing that you might ask me is that what I am doing here, I am only trying to maximize the likelihood at the end of the whole chain rule, right? So I start from time t, then I move backward on my chain rule. My final purpose is that at time 0, I have a sample which is coming from the same distribution as my data, right? So what I'm not doing, I'm not really taking care of people in between, right? I don't care that at time, for example, t minus 1, I have exactly the same marginal distribution, right? I didn't write down that one, because if I wanted to do this, this is, for example, the marginal, this is the marginal distribution for time t minus 1, right? If I want to do that, then this guy should be exactly like the noisy version of my data, right? But the point is that why should I do that, right? I wanted to do this on SDE, on the diffusion process. I wanted to do this because the reverse diffusion was telling me if you can do this, then at the end of the day, you are going to end up with data, right? But right now, I am putting my objective to have my final distribution to be like the data distribution, right? So there's no reason that I be obsessed about the samples in between, right? And eventually, the thing that is happening is that theoretically, they are not the same. Because if you want to make them exactly the same, then you're going to get into a bit of trouble, theoretically, right? But we don't care at all. You got the point that I said? So the end point is that what you do, you are only caring about the guy which is coming at the very end of your chain rule, right? And you don't care if that at time 1, the sample that you get is exactly the same sample or the same distribution as the one you had in your forward pass, right? The point is that in practice, what is going to happen is that at the very far away from the beginning of time, you don't have exact match, but as you just move toward the beginning of time, you get a better match, right? And if your model is trained perfectly, then at the beginning of time, you're going to exactly sample from data distribution. Everybody's cool? Questions? So you got the idea, right? So I want to do maximum likelihood. This is a typical thing. But the problem that I do have right now is that I cannot compute that massive integral, right? Everybody's cool? OK. So we cannot do that massive integral. This is a very massive integral. This is computationally hard because I need to integrate over all xt's. But there is a way around it. Do you remember anything we had in the course where we also got trapped with this massive integral? Do you remember when we wanted to just write down the maximum likelihood estimation for the output of the decoder of one autoencoder, variational autoencoder? At the beginning of chapter 5. So at that point, we said like we have one Gaussian sample process that was our latent. We sample that Gaussian, we pass it through decoder, we get the output. This was a Gaussian mixture model, right? And if we wanted to know what is exactly that marginal distribution, we needed to compute a massive integral, right? And we said we cannot do this. Then instead of doing this, what we did? What did we do? We just computed a lower bound, right? So we just came up with the evidence lower bound. And you eventually can do the same thing here. Because again, you have your P of x0, which is being your evidence. And the thing that you can do, you can take the same trick as before to find a lower bound on this. That lower bound is potentially very tight. When you maximize that lower bound, then you're going to touch this point, right? So instead of maximizing the likelihood, you are going to maximize that evidence lower bound. So this is going to be the trick. We are going to do exactly the same thing as we have done in the variational autoencoders. But the point here is that I'm going to do it quickly now, because you do know what is variational inference. OK? So the main idea here, if you want to just write it down, let me just clean up things a bit. So what I'm going to do from now on, this distribution that you see, xt minus 1 given xt, and so on towards very beginning, I'm going to show it by x0 to t, right? And I'm going to drop that time, that t, because I guess you see it immediately. And then I put this w here to indicate this is my model, right? So this is the distribution described by the model that is moving on the chain rule, right? So I'm going to call it the joint distribution of the very beginning to the very end points on the chain rule, but we are now talking about the reverse chain rule, right? So we start sampling at the end, and then we move towards the beginning of time, right? So this is the joint distribution, and the thing that I want to do is that I want to just integrate it over everything but x0, right? So I can write it down in this form. So I want to just integrate this guy over dx1 to t, right? x0 is not there, but 1 to t are there, right? Everybody's clear? So that's going to be a shorter notation now, right? And now, I want to just compute this integral, and we had it before, so let's just try to do the same thing as we have done before. So do you remember when we started with variational inference, what did we do? What was the first step we did? It was importance sampling, right? You have it here, right? Importance sampling. So I'm going to do again the importance sampling, right? What do I say? I would say, okay, I want to just compute this logarithm, which is logarithm of this integral. The thing that I can do, I can look at the term inside my integral. I can divide it by one distribution, multiply it by one distribution, right? So let's say I have this distribution lambda. This distribution is conditioned to x0, right? Why it is conditioned to x0? Because my evidence itself is computed at point x0, right? So I am computing the evidence for one particular data sample that I have, right? One particular x0. x0 is one of the images that I have. So my distribution lambda is potentially conditioned to that x0, right? If I just find the right lambda, then it's going to give me the right samples, and those samples are going to help me compute this integral, right? Now, looking at this expression here, I have integral. I have one distribution over x1 to t, and I take the integral over x1 to t. What is this integral? Integral of something, distribution dx. What is it? It's expectation, right? So I can write it down as an expectation, right? So I could say this term is expectation of this fraction, right? So I can say this is logarithm of the expectation of this term, right? This was the same thing we did when we started with variational inference. At that point of time was new. Now, hopefully, you got a bit used to it. So this is not going to just make you wonder too much, right? OK. Now, what I want to compute this expectation. Why we are happy with the expectation? We talked about it too much in this course, I guess, right? If I have this lambda distribution, then I can take samples from it. I can put inside this term, and then I average it out. This is an estimator of the expectation that I want, right? OK, that's good. Now, next thing that I can do, I have logarithm of expectation, right? How does the logarithm function look like? The logarithm function looks like this, right? If this is x, and I want to plot log of x, it's going to look like this, right? This is log of x, right? Now, is it a concave function or a convex function? It's a concave function, right? Now, if you have a concave function, if you take 2 points, and you average the points, right? This is the point x1. This is the point x2, right? If you average these points, this means that you are here, right? This is the expectation of your x. And if you look at the expectation of your x on your function, so this point is logarithm of the expectation of x, right? But if you compute the logarithm at the expectation of x, if you take the expectation on the logarithm, you're going to end up at this point. This is going to be the expectation of the logarithm of x, right? And this is the Jensen inequality, right? It's going to tell you that logarithm of the expectation, this guy, is always more than the expectation of the logarithm, right? So we can use this inequality to just bound this guy, right? Logarithm of the expectation, I can take logarithm inside, and then I'm bounding from below, right? So I can write it down in this form. So I could say that the logarithm of the expectation is larger than the expectation of the logarithm. Now, looking at this term, now I have an evidence lower bound, right? I have one lower bound, which is only depending on that particular point x0, right? And this is bounding my log likelihood, right? Now, given that that particular Jensen bound can be tight. This bound can also be tight, right? So meaning that if I just go ahead and play with this W in a way that this evidence lower bound is maximized, hopefully I'm going to hit exactly the likelihood term, right? So I don't need to explicitly maximize the likelihood. I can implicitly maximize it by maximizing the evidence lower bound, right? So this would be the conclusion. I can do implicit maximum likelihood estimation here by just maximizing the evidence lower bound, right? Questions? Everybody got the idea? So this guy is the distribution that is given for the data coming out of the whole reverse trajectory by my model, that I want to make that guy looking like my data distribution. To do that, I do not maximize the likelihood. I just maximize this ELBO. And this ELBO is something that I can compute, right? Because I do have this distribution. This PW is given by my model, right? I just need to move on my evidence, right? On my chain rule, right? And that lambda is something that I have specified, right? Again, I have it. I can sample from it. Okay? So I compute this expectation. And this is going to be an estimate of the likelihood, right? Or lower bound on the likelihood. And then I try to maximize it, right? I find the right W, then maximize this guy. Questions? Everybody's cool? Like, I find it today a bit awkward between us. Like, you're not very happy with what we're doing. I mean, I do understand it's a bit too much, yeah. But think about the ultimate, right? The ultimate point is that you do know then diffusion models very concretely that many people don't know, right? So this is the good faith to just study this, right? Yeah, but I do get it. It's too much of details, yeah, for this particular one. I mean, even if you read the paper, it's too much mess, all of the papers, because people have always a hard time to present this kind of idea. Okay. Okay, so now, one question here. When we were doing the importance sampling in variational inference, then what did we conclude? What was the best distribution that we could have to do the importance sampling? Do you remember that? No worries if you don't remember, but if you can remember, that would be great. Do you remember what was the best distribution we could put? I mean, in variational autoencoders, what we did, we learned that, right? We just trained an encoder, and that encoder was somehow mimicking that distribution. But do you remember what was the idea? What was the best one which we could have? Do you remember the posterior distribution? So we wanted, at that point of time, we wanted to find out what is the best distribution that we can sample latent with, given one particular x0, right? And then we wrote down a few lines, and we concluded that the best sample, the best distribution, is actually the posterior distribution, the distribution of latent given x, right? But the problem was that we could not compute it, right? It was very hard to compute. We put one neural network there to do it for us, right? So that encoder was supposedly trying to mimic the posterior distribution of the latent. You sample from that, then you decode it, right? That was the idea. So moral of the story, this lambda here should be actually the posterior distribution. Okay? But good news here is that since we have the forward diffusion, we can write that down very easily. So we don't need any extra neural network anymore to learn that posterior distribution, right? So this is the whole twist. This is the whole source of power that this model has. Okay? So the key point here is that the best distribution that you could have is the posterior distribution. And this means that I need to know the distribution which is eventually described by the forward process that you had, the forward diffusion. Starting from x0, you were just noising everything, right? With that forward process or diffusion, you're gonna have one particular, process from x0 to x0 to xt, right? Now, if you can compute the posterior, this particular posterior, then the thing that is going to happen is that you should replace that lambda with the posterior, and that posterior is going to be the best distribution you can sample with, okay? But the point here is that we can actually write down the posterior here easily. Just let's try to open it up and see how it looks like. Now, when first of all, can you open this up for me? Can you open it? How do you open it if you want to open it? The easiest way you can do it. Chain rule, it's going to be x1 given x0 times x2 given x1. You don't need x0 anymore because Markov chain, right? x3 given x2 and so on, right? But you do know that on your reverse Markov chain, you are moving the other way around, right? So if you open up this way, open this guy this way, it's not going to be useful for you. It's not going to end up with a very good term. So what I'm going to do, I'm going to open it up the other way around. Meaning that I am going to start from the very end of time, xt, and I move backward in time, right? But now that I move backward in time, I cannot simply get rid of everything, right? Because in the forward diffusion, I have Markov chain, right? x2 only depends on x1, x3 only depends on x2, and so on. But if I'm looking backward now, x3, theoretically it depends on everybody, right? When I have x2, I don't need anyone more, right? But if I have anyone forward, then I need all of them, right? Because I cannot write it down explicitly, right? So I cannot simply throw away everything, but I can open it up, right? So I can say the posterior distribution is xt given x0 times xt minus 1 given xt and x0, and so on, right? If I am at the particular time t, then I'm going to go one step backwards. So again, you just look at this, think of this one. So you have x0, it goes to x1, and so on until you get to xt minus 1, xt, and then you keep on going till you get to the last guy. Now, you said xt, then you condition to xt minus 1, and so on till you got here, right? When you want to write this one, then you're going to say q of xt minus 1 given anything that you already had, right? Which is going to be xt to the last time interval you had. And, everything was initially conditioned by x0, so I'm going to put x0 as well here, right? Everybody's clear? Questions? No question? So, I can write this guy down in this form, right? So it's going to be q of xt, the last guy given x0, times all the backward or reverse posteriors that I could write. Now, one question here before we start to get lost. This q, xt given x0, do you have it or not? Do you know what is this guy? Tell me, what is it? It's a Gaussian, right? We just derived this, right? We said that every single time we can describe the direct connection from x0 to that time, right? We did it together, right? So that first term, I do have it, right? This is no problem. The thing that I'm not clear about yet is this guy, right? Everybody's cool? Questions? So, sorry. If I can come up with an expression, if I can come up with an expression for every single of those terms inside the product, then everything gonna be over, right? I can write down this posterior. So let's do it right now. One thing that I'm gonna do, I want to just find out what is this particular conditional distribution, right? And now I would write down this xt to the end of time. I'm going to write it down xt, small t, and xt plus 1 to the end of time. Okay? Nothing. I have done no magic, right? Just opened up this term. Okay? The magic is to come. Okay? Okay. Now, the next thing. I want to just look at this term, okay, which is exactly the same term. So I put it inside a box here for you. Now, I'm going to multiply it with this distribution, right? So this distribution is giving me this red term, I put it here, given x0 and xt, which are here, okay? When I multiply these two, what is happening? Exactly. This one is a red term given these two times xt minus 1 given the 2 and the red term, right? So I can say that this product here is the joint distribution of t minus 1 and the red term given the other two. Everybody's clear? So it's just a chain rule, right? If you start from the green term and you just write down the chain rule, starting with the red term. So you write red term given the other two times xt minus 1 given red term and the other two, right? That's a simple chain rule, right? Now, what is this guy? Can you tell me what is this guy? So this is x of, maybe I keep on writing here, xt plus 1 to xt, right? It is the distribution of anyone from here to the future, so anyone from here to the future, given this guy and this guy. If I want to talk about anything in the future, do I need to know x0? No, I just need this guy, right? So it's going to be p of this guy given this one, right? Times p of the next guy given this one, right? Times p of the guy after given the previous one. Huh? So you can write it down in form of this product, right? Each time it's going to be q of the next time given the previous time, right? Everybody's cool? Everybody's clear? So this blue term is simply a product. I don't need x0 because I'm moving in the forward time direction, right? Now, next thing, I can open up this same term, the green term, differently, right? Instead of starting with the red term first, given the 2 times xt minus 1 given the remaining, I'm going to start first with xt minus 1 given the 2 times red term given whatever I had, right? It's again the same green term here, but now I open up the chain rule differently. Everybody's clear? Right? Now, look at this term, the first term here, this guy. How can you write it down? This is again the distribution of anything after t, right? Given xt, xt minus 1, and x0. So this guy is also now here. But do I need these two? No, I can throw that away. Again, xt is the only thing I needed, right? It's going to be q of this one given this one times q of this one given this one, and so on, right? So this first term is again the same product as I have as above, right? Correct? Now, look at this term. I have the green term, this one, exactly same here and here, right? This is once this blue product times $1. The other time is the blue product times another box, right? This means that the boxes are the same, right? Everybody's clear? The boxes should be the same, right? Now, if you look at the boxes, the first box has x of t plus 1 to t, but now this other box does not have it, right? It only has xt and x0, right? This is much easier than that one, right? So I'm not going to use this one, which I needed at the first place. I just use this one, right? Everybody's cool? So, moral of the story, if you want to just compute this one, okay, this posterior distribution that you want, you eventually need to just look at the time t, and time 0, you don't need any other time, right? So this is going to simplify everything significantly. And the reason is because, I mean, when we wanted to just write down that term, if I want to compute this guy, I do know that I'm quite short in time, so I'm going to just give you a brief overview how you can compute this. Then we're going to do it next time again. So if I want to just compute this one, I can simply do it this way. I want to compute t minus 1 given xt and x0, so I'm going to write down the definition, right? So it's going to be the joint distribution divided by the distribution of xt and x0, right? These two distributions needs the data distribution to be known, right? But what I can do, I can again write down the chain rule, right? If I write down the chain rule, this is going to be the distribution of xt minus 1 given x0, time data distribution. In the denominator, I have again xt given x0, data distribution, right? The data distribution is going to cancel out, right? The only thing